Hello, this is Dr. Muhammad, and this is another video under design of steel structures according to AISC. We are still talking about the compression members, and today we are going to talk about part 4. The contents of today's video is going to be related to the effective length. I'm going to talk about effective length more in depth, and then I'm going to take example. After that, I'm going to mention about the approximate effective length factor, and after that I'm going to talk about the effective length moment frames, or effective length for moment frames. I mean that for the case of columns. This is the case where that we are having side sway permitted, and I'm going to talk about the effective length of columns in case of the braced frames, which is side sway not permitted. Okay, now let's go to the next slide. So actually here, as we said that we are going to talk about more about the effective length. So before doing anything, we want to understand that whenever we have a column, as you can see here, we are like having two principal axes for this column. Okay, so these two principal axes, the column can buckle around any or about any one of them. So if we have a compression member, okay, and this compression member, if a compression member is supported differently with respect to each of its principal axes, the effective length will be different for the two directions. As you can see here, we have a column. This column is having X and Y axes. If you look to this column cross-section, which is I cross-section, it is going to buckle, if you look here, around Y axis, and the length here is going to be this length, which is the half of the column length, which is 12 feet, for example. And also here we are having the second half of the column, which is another 12 feet here. So this means that our column is going to be as if it is going to be separated by this girder or this beam, and the effective length is going to be half. This is around Y. However, around X axis, you're going to find that the full length is going to work for us. So the two direction or the two directions, they are not the same. So this is how, or this is the X-axis buckling. You're going to find that this column is going to buckle. I was only giving the example that is half of the total length is going to work for us here, but actually for this end conditions, the inflection point is going to be halfway through of the first story, for example, and the second story. So we're going to find that the effective buckling length is going to be half. Okay, it is like the distance between half of the upper story or from the middle of the upper story to the middle of the lower story. Okay, and this is how it will work for the y-axis. Okay, we're going to find that the buckling length is going to be like less than even the half. Okay, so this means that this is what I want to highlight here, that the effective length will be different for the two directions. This is something important to keep in our mind, that the buckling length will not be the same for two different directions of the column. Okay. Generally speaking, a rigid or fixed condition is very difficult to achieve. This is very true, because it is difficult actually to achieve the fixed condition. Okay, in reality, actually this is how we can obtain, if we are talking about like rigid connection, we can obtain it by this kind of connection, but still full rigid, full fixed connection is very difficult to obtain. There is still some rotation is going to take place here. Okay, unless some special provisions are made, so we can obtain the rigid or fixed connection or fixed condition with under special provisions. Ordinary connections will usually closely approximate a hinge or pin connection. This means that the most common one is like hinge or pin. Actually, in reality, we are not going to achieve these ideal cases or these ideal conditions, which is related to the rigid or fully fixed or fully hinged. We are somewhere in between. So we are going to be like partially fixed, for example. But again, to make it easy for us for calculations and formulas and so on, we are going to assume like fully hinge or fully fixed. And here we are going to talk about the pin end conditions. Okay, this is the common case that we are going to deal with. Unless that we have a frame, for example, then the connection is going to be, or the condition of the end condition is going to be judged by the flexural stiffness of this girder with respect to the column stiffness, as we are going to see later. Okay, so this is an example for the rigid connection. This is an example of the pin connection, as you can see. In reality, you're going to find it here. This is the rigid or fixed connection. This is like a base of a column, as you can see, very heavy, and seems that really we are maintaining or putting the special provisions, as we said here, which is like increasing the column base and putting very huge like anchor bolts here and with the stiffeners and so on. So this, yes, this gives to us maybe a fully fixed connection. On the other hand, we can have some case like this, which is related to the hinge or pin connection. As you can see, it is allowed to rotate here. It is allowed to rotate. Okay, now let's go to the next slide. Look to this figure, and this is what I was talking actually about in the beginning, okay, when I was like referring to this and saying like half and half and so on. Actually, it doesn't apply directly here, but here we are going to understand what I meant by this. If we have a column, as you can see here, this column is like supported at halfway through or in the middle or in this floor, at this level of the floor. We're going to find that the column length is divided, okay, with 13 feet each. And we are going to symbolize this beam or these girders or these beams with like pin connection here. So the buckling wave of the column is, if we assume that it is hinged at the top and hinged at the bottom, then the buckling length, as you can see, going to be like KL of this length is going to be half of the total length of the column. So effective length is going to be 13 feet if we're talking about the column, because the column is, say that this is the web, these are the two flanges here, okay? This is how we can see this. So we are having something here and here, which is these girders or these columns. They are supporting the lateral displacement of the column on this direction or in this direction. We call this minor axis buckling, which is going to be KL, going to be 13 feet. However, here around the major major axis buckling, you're going to find that the column is free to buckle from here to here, from the top here to the bottom foundation, as you can see. And we have the column is going to be, this is the column here, okay? So this means that it is supported here and here, but however here and around the strong axis, the buckling length is going to be double, or we can say 13 feet with adding on them another 13 feet, which is the total length, okay, the total length, because we do not have any lateral support here. So it is as if that we are having pin connection, and the total length KL is going to be 26 feet, okay? So this is, if we're talking about wide shape, it was a wide shape here, is used as a column and is braced by horizontal members in two perpendicular directions at top here. These members prevent translation of the column. These members, we're talking about these members, they are not going to allow the member or the column to go laterally. okay, in all directions. So it is like controlling it to go in this direction and also like perpendicular to the white screen or this screen, okay. These members prevent translation again of the column in all directions, but the connections, these connection, we didn't mention about the details now about this connection, permit small rotations to take place. That's the point here. As long as there is permission for small rotations to take place, this means that we are going to resemble this connection as pin connection. Under these conditions, the member can be treated as pin connected at the top. As we said here, it is pin connected at the top. For the same reasons, the connection to the support at the bottom may also be treated as a pin connected. So here, this is a pin connected as well, or pin connection. Okay, so again, as we said many times, we cannot control the rotation, even that we are putting some details for it, but we cannot control the rotation. Here we are going to assume that it's pin connections. Okay. Now let's have an example about what we have discussed up till now. So let's assume that we have a wide flange 12 by 58, 24 feet long, as you can see, column. Okay. And it is pinned at both ends, pinned here and pinned here as well, in the weak direction at the third point. So it is like pinned, sorry, it is pinned at the top and bottom, which is like around X direction, and around Y direction it is like connected or in the weak or braced in the weak direction at the third point. Means that 1/3 of the length is like laterally supported here and laterally supported here. If we're going to look to it as 3D or isometric, you are going to find that we have this is x-axis, for example, and we have this is y-axis, okay, and then the rotation around this strong axis around x-axis, okay, is going to be, or the buckling length or L is going to be 24. The unsupported length is going to be 24 feet. However, that around y-axis it is going to be 1/3, 1/3, 1/3 here, because we have like support here or lateral support here, which is like resembled here by these pin support or the hinge supports here. So we are going to check both directions. So we have, okay, we have the cross section is wide flange, and we know it. We know all the properties of this section. We know the length, and we know the yield, F yield. It is F yield equal to 50 ksi, and we want the available compressive strength, So first of all, we are going to calculate the slenderness ratio, KL over R, okay, around x-axis and around y-axis. The weak and the strong axes are going to be calculated. So we have Kx times L. Kx here is 24, which is the total length around the strong axis, x-axis, okay. So here, if we have this is like X, for example, here, and if we have this is the weak axis, which is Y. So Kx, which is 24 times 12. K here, it is 1 because we are talking about pin-pin connection. So we have K equal to 1 over Rx equal to 5.28. From where? This is from, exactly, from the dimensions and properties table. So stop the video now and go to the tables, check this value. After that, you're going to check the other direction around y, ky also it is 1 here because still we are talking about pin, okay? So it is pin. So we have 8 times 12. This is for the conversion from foot to inches, and then this is ry. Go to the table, dimensions and properties table for this cross section, wide flange 12 by 58. And check these values. Then we're going to find that our kxl over rx is larger than ky over l. Can you imagine? So the strong axis is going to be vulnerable. Okay, this means that larger value controls. For LRFD, we're going to use table 422. If you do not know about the tables, please revisit the previous two videos and you are going to understand quite well about this table, okay, because we have explained it in detail before. Then KL over R, it is 54.5, which is the larger one that we're going to use here. And from the table, you are going to find that phi C times FCR, it gives us 32.24 KSI. Please also go now and stop the video and check this value. Based on this, our nominal strength Pn times phi C or phi C, it is going to be phi C times FCR area gross, which is going to be 17, so 36.24, okay, which is this value already we have, times area gross, it is 17. Also, this is from the table. Go and check it from the table. Then you are going to find that this is the design strength for LRFD. It is going to be 616 kips. Okay, so now what we can get from this example, simply that we need to check both direction. And in our case, it was, as we are expecting, that the weak axis was not vulnerable, however that the strong axis was vulnerable. Okay, so the design strength was controlled by the buckling length around the strong axis, not the weak axis. Okay. Now let's go to another example, and we are going to use available strengths from the tables using Rx. Okay, this is using Rx. Why Rx? Because commonly our tables we are using Ry. So here we are going to check how to use the tables if we want to check for KXLX over Rx. Okay, so we want to check about this, how we can use the table or the tables in this case. Okay, so I'm going to explain about this right now, and I'm going to talk about the rationale behind it. So the available strengths given in the column load tables, okay, we have explained about this in the last video. Please go and check this these tables in the previous videos, are based on the effective length with respect to y-axis. As we said, we're talking about y-axis whenever that we are checking the wide flange or the cross section. We are talking about the y-axis. We have x-axis and y-axis. Okay, so we are having the effective length with respect to y-axis. A procedure for using the tables with KXL, however, can be developed by examining how the tabular values were obtained. So we are going to start with the value of KL. The strength was obtained by a procedure similar to the following. We put KL was divided by RY, which is related to the around Y, okay, or about Y. So it is, we have obtained KL over RY. Then we compute FCR, and after that the available strength is phi C times Pn for LRFD, or Pn over the omega for the ASD, right? That's where or how we were using the tables, right? Thus, the tabulated strengths are based on the values of KL being equal to KYL. That's right. This is what we use. This is the one of the conditions that we're using. If the capacity with respect to x-axis buckling is desired, the table can be entered with this value, which is KXL over the ratio between Rx over Ry. Take care of this. So we are going to obtain Kx times L over the ratio. And the tabulated load will be based on, it is going to be KL over Ry, which is this equation here over Ry. Okay, this is Ry and this is Ry. And the numerator here, KL, it is going to be what we have like assumed here. Then the output is going to be KXL over Rx. Okay, so how What is the key here? The key is we want Rx over Ry to be readily available. So the ratio of Rx over Ry is given in the column load tables for each shape listed. And if you remember that I have mentioned about this in the last video. Okay, so Rx over Ry is available in the table. Okay, I think that we are ready now to take one example and check what we have mentioned. The compression member shown in figure 4.12, this is as you can see it here, is pinned at both ends. So it is pinned at this end here and the bottom, it is pinned, and supported in the weak direction at mid height, and supported at the weak direction at the mid height, as you can see with this this girder. Okay, as you can see it here and here. This is the beam that is being used to support the column in the weak direction. A service load of 400 kips with equal parts of dead and live load. This means that dead is 200 and live load is 200 as well. Must be supported. So use F yield equal to 50 ksi. This is the yield of the steel cross section, and select the lightest white flange shape. So we are going to think about, whenever we have a problem like this, we need to think about the buckling length. What is the buckling length that we are going to use? Whether around the weak axis, okay, which is going to be 9, or around the strong axis, okay, which is going to be 18 feet double. So this means that we need to check both. We need to check both. So factored load, in this case, we start with the factored load because we want to start with like one number in the beginning, and then we are going to check others. Okay, I mean that check the shapes available. Okay. Okay, we want the lightest white flange shape. So assume that first of all the factored load is going to be 1.2 200 plus 1.6 200 because we are governed with gravity loading only, no wind and no earthquake. So we have 560 kips. Assume that the weak direction controls, okay, we're going to assume only this, weak direction controls, and then we're going to check for the strong direction. And enter the column load tables with KL equal to 9 feet. So now stop the video and go to the tables, okay, with KL equal to 9 feet, okay, and check first with the wide flange with 8, okay, 8 inch depth, okay, and check beginning with the smallest shapes. We have, this is wide flange with 8, depth with 8. The first one found that will work for us is going to be wide flange 8 by 58 with a design strength 634. Again, I have explained this many times in the last video and the last previous videos. So please stop the video and go to the tables and check this value. Okay, if you have no idea, again, I'm saying this again, go to the previous 2 videos and check how we can obtain this value based on the tables. Now check the strong axis. Okay, we have assumed here the weak direction. Now we are going to check the strong axis. So it is going to be kx over kxl, which is 18 because we have k here. It is 1 because it is pin connection. So we have here 18 over rx over ry, 1.74 from where? From the table. It is given for us in the table. So please check it also. So now we have this new slenderness ratio is 10.34. Okay, or the effective length now for us is going to be 10.34, which is larger than 9 feet, right? Here we started with 9 feet, but when we check the strong axis, we found that it is going to give us the equivalence of it is going to be 10.34 feet. This means that Kx times L controls for this shape. That's right. This means that the strong direction, okay, is going to be, the strong direction is going to control here. I mean that the effective length for it. Now enter the tables with KL equal to 10.34. Now already we found that the 9 was giving us this value, 634. But actually we are going to check for the real controlling value, okay, the real controlling value. So we are going to check with 10.34. Enter the table again for wide flanges and check how much strength is going to be available, okay, that is going to exceed this 560. So when you enter the table with KL equal to 10.34 feet, a wide flange 8 by 58 has an interpolated strength of, yes, 596 kips, which is larger than 560, which is the original one that we were, or the required strength, right? Okay, now remember how much this shape weight, it is 58 pounds per foot. Remember that we are searching for what? Lightest. Okay, so now for wide flange with the depth of 8, we found that the lightest one that is going to work for us, it is 58, okay? 58, okay. Now let's investigate the wide flange with nominal depth of 10. Try W10 by 49, okay? Okay, with a design strength going to be 569. Why we chose this? Go to the table and you will understand why it is like this, because this is the lightest shape that is going to provide a value of strength, design strength, that is larger than 560. So we found that it is going to be 569. Okay, this is for what? Using what? KL equal to what? 9, exactly. Now we are going to check, we are assuming that KL with the weak axis is going to control, right? So now we are going to check what? The strong axis, which is KL around the strong axis. And when we check it, KL over R, the slenderness ratio, it is going to be 18, as we have done before, over Rx over Ry from the table. It gives us 10.53. This means that we need to check KL, okay, KL for having 10.53, which is this value. The slenderness, okay, KL over R here, the slenderness ratio here is larger than a 9. This means that we need to use it. We need to use this new controlling slenderness ratio. Then what we are going to do? Exactly, we are going to enter the table with 10.53, exactly, and then obtain the lightest wide flange with nominal depth of 10 that is going to have design strength that is, let's go back again, yes, 560 or larger. So we want something to be 560, okay, or larger than this. So the lightest wide flange 10, okay, with an interpolated design strength of 596, okay, which is larger than the required strength, is going to work for us. This is the lightest shape with nominal depth of 10. Continue the search and investigate another wide flange. We checked 8 nominal depth, 10, and then 12, and then we have 14, right? This is how we are going into the table, as we have mentioned before. Okay, so now we know about 8 and 10 already, and now we are going to for the 12. Continue the search and investigate wide flange with 53. Okay, why 53? This is the lightest cross section that is going to provide design strength 610, which is higher than the required strength, right? For KL, again, we start with KL 9, always 9. And then we are going to investigate for the other strong axis or direction. So kx times L, which is kx, this is the strung around the strung axis, kx1, L is 18, over the ratio. From the table we can obtain the ratio. From the column tables you are going to find it 8.9. Okay, so now this is 8.53. However, that this one, it is 9. So this means that 9 feet is going to control, not 8.93. So for the wide flange with nominal depth of 12.5 times 53, the slenderness ratio around the weak axis is going to control. So we are going to have 610, our nominal design, our design strength for this cross section. So this means that ky times L controls for this shape, and phi c times pn equal to 610 as we have obtained it before. Okay, so we're not going to use this. Definitely this slenderness ratio is going to provide something something that is going to be like less, okay, less than 610. Okay, so I mean that this is the for 9 feet, this is the design strength that is corresponding to it. Okay, I mean that this 9, because this is considered to be the slenderness ratio that is going to control. Okay, so if we have less slenderness ratio, this means that it is going to be different than this 610, and we need to not to consider it, because this is the we can say the critical slenderness ratio that should be used. The critical slenderness ratio that should be. Okay, what I meant here, maybe I said that in a wrong way. Actually, whenever that we have less slenderness ratio, this means that the design strength is going to be higher. So we should check the slenderness ratio that is higher in order to get the lowest design strength. Okay, and then determine the lightest weight for W14. And as we said that we are going now to W14. The lightest one with a possibility of working is W14 by 61. Why? Because this is, if we use 9 feet, we are going to find that it is heavier. Okay, it is going to provide, if we use the tables for 9 feet, it is going to give us 14 by 61. It is heavier than the lightest one found so far, because all of what we have found, it was like in the range of 50s. Now for W14, we found that the lightest one for 9 feet, for example, is going to be heavier than the previous ones. This means that 14 is not going to work for us. 14 is not going to work for us. So it is heavier than the lightest one found so far, so it will not be considered at all. This means that checking all the previous ones, let's go back here. We have 58. This is for nominal depth of 8. We have 54 for the nominal depth of 10, and we have 53 for nominal depth of 12. So as you can see, the lightest one is wide flange with nominal depth 12 by 53, and this is what we are going to use. Okay, so again, just recapping of what I have said here, or what I have discussed in this example, we want the lightest wide shape, right? So what we are going to do is simply we're going to check for 8, 10, 12, 14. These are the nominal depths for wide flange. Then we are going to use the table for each one of them, and we are going to enter the table with 9 feet first, which is the weak axis buckling length, and then we are going to check it. Then we're going to check the other like strung axis slenderness ratio. Okay, we're going to check the second. If it gives us higher value than this 9, this means that we are going to use the corresponding design strengths for this case. If not, then we're going to use the design strengths corresponding to 9 feet. Okay, and the same for 10, the same for 12, and the same for 14. From all of these, we're going to get the lightest one. Okay, so this is what we have done exactly. We started with wide flange, nominal depth 8. We found that 58 is going to work for us. Okay, this is 58. I mean that it is the lightest shape that is going to provide the design strengths. We checked first 9 feet. Okay, so the 9 feet gives us this 634 something kips. Here we found that the other one is going to provide us 10.34, larger than 9 feet. Then kx, strong axis, would control. When we checked it with 10.34, we found that it gives us 560. Okay, not 634. This is not the right one. The cross section is going to fail by this one. The cross section is going to fail by this one. Okay, and then we have done the same for wide flange with nominal depth 10, and we found that we are going to check first it's the slenderness ratio. We found it 10.53, and based on this, it is larger than 9, so we're going to enter the table with 10.53, and then we are going to obtain the design strength. We checked it. We found that the lightest shape is going to be with 54. Then we repeated the same procedure for nominal depth of 12, and we found that at this nominal depth the strong axis slenderness ratio is less than 9 feet. Then 9 feet would work for us from the table from the first trial, which is this one, and the weight here is 53. Then after that we checked for the case of 14, nominal depths of 14, and we found that it is going to give us very heavy cross section, so we excluded it from the beginning. We didn't check it. And then our final lightest cross section is going to be this wide flange 12 by 53. Okay. Now let's go to the next part, which is related to the effective length for columns and continuous structure. What I mean by the continuous structure is, like, if you want to call it like frames, for example, yes, you can call it something like this if we're talking about frames. Okay, but continuous structure here means that any column that is part of like larger structure is considered to be one part of continuous structure. We have many columns and we have many beams framing into one another, and we want to understand more about it. Okay, so now first of all, I'm going to study like 3 different parts of this. First is something related to the approximate effective length factor, which is something like really it's approximate, and it is going to be focusing on the end conditions only, whether it is in a continuous structure or not, whether it is like isolated or individual column or connected to other elements. If we are sure about the end conditions, like going to be fixed, for example, 100% sure, then we are going to use these approximate values for effective length factor, okay, without thinking about whether it is in continuous structure or not, but they call it like this isolated columns, where that we know the end conditions very well. Okay, so this is the buckled shape of the column, okay, which is shown in the dashed line here. If we have hinge, if we have fixed, so the theoretical K is going to be 0.5. However, what is recommended design value when ideal conditions are approximated is 0.65, means that we are always taking into consideration the ideal conditions, the reality conditions. Okay, this is the case of B, which is hinged fixed, supposedly to be 0.7. Okay, and for guided fixed, it is going to be 1, and for hinged, it is going to be 1 as well. And here for free fixed is going to be 2, and for guided hinged is going to be 2. Okay, so this is the end condition code that we have used: rotation fixed and translation fixed. This is rotation free and translation fixed, and this is rotation fixed here and translation free, and the last one, it is like pan rotation free and translation free as well. Okay, so this is, you can find this table as C-C2.2. Okay, in the specification you can find it. For isolated columns that are not part of a continuous frame, okay, if we say this is isolated column, okay, which is not part of continuous frame, or if it's part of a continuous frame and we know well what is the end conditions. If we have, for example, a continuous frame, but the girder is so huge compared to the column, and its stiffness is very high, then we are going to say that this column as if it has fixed condition, okay, as if it is fixed at the top. So this means that if we are having a well-defined end condition, then we can use it. Then we can use this approximate value. In reality, actually, you're not going to find that something, or you're not going to find these end conditions to be fully like acknowledged. You're going to find that always there is a debate about what is the right end condition to be used. Okay, because we cannot guarantee 100% it is going to be fixed, or 100% is going to be like hinged, like here, as we said before. Reality is always different, but this is considered to be an approximation that is going to provide you some conservative values and going to put you in the safe side. Okay. Okay. And commonly, whenever we are talking about the buckling length, so this is what I have like mentioned here. If we're going to have hinged, the most famous, we can say these are the most famous end conditions that you can see if we're going to talk about hinged. So this is the buckling length here. If we are going, which is going to be 1, as we said. If we have like fixed free, this is also a very common case. You're going to find buckling length is going to be double of the length, because the buckling wave is going to be like double the length. Okay. Buckling length is going to be double. And if we have like fixed, so take it as 0.5, maybe we forgot the 0.5 here, so it's going to be 0.5. And if we have like pinned and fixed ends, then K is going to be 0.7 here. But anyway, if you want to be very accurate, you should use this table. Okay, you should use this table C-C2.2, and this is the accurate one and the most accurate if we are talking about approximation for the end conditions. Okay, now let's talk about something else which is related to the side sway permitted case. Side sway permitted. Effective length of columns in case of continuous structures where the side sway is permitted. Okay, non-braced frames, for example. Like moment frames, as you can see, many cases we are having moment frames where that we do not have any bracings. And we have lateral loading here. Okay, we have gravity loading and we have lateral loading. So if you're going to talk about, one column here, for example, which is AB, for example, then you're going to find that the end condition cannot be defined well. It is going to be defined based on the girders framing into it, and in the same time, because this structure is side sway permitted case, this means that whenever there is lateral loading, you're going to find this point is going to laterally move, right? That's right. So this is the first case, side sway permitted. The rotational restraint provided by the beams or girders at the end of a column is a function of the rotational stiffnesses of the members intersecting at the joint. That's right. We are having different rotational stiffnesses of the members. Okay. The rotational stiffness of a member is proportional to E over L, which is the Young's modulus over the length of the member, where I is the moment of inertia of the cross-section with respect to the axis of bending. So how we are going to find a way for this, how we can find like what is the end condition and how we can obtain K. It is going to be problematic for us, right? So in 1992 there was research by by some researchers. Okay, they show that the effective length factor K depends on the ratio of column stiffness to girder stiffness at each end of the member, which can be expressed like this. So we're going to use this word or this letter G, capital G, which is going to make or to give us the ratio between the sum of the stiffnesses of all columns at the end of the column under consideration. This is the numerator, and the denominator is going to be sum of stiffnesses of all girders at the end of the column under consideration. If we are talking about the same material, which is concrete or steel, we are talking about steel here, so we are like having summation of sigma IC over LC over IG over LG. Okay, so we are having this this ratio. Okay, we are having this ratio. Okay, and this is EC and EG. It is like E, which is the modulus of elasticity of structural steel, because we are talking about steel here, and they are having the same Young's modulus. Okay, okay. Now, whenever that we're talking about different like end conditions based on this ratio, we are going to use what we call it the alignment chart K. Okay, so if we go back here, if we're talking about this A, B, which is here A, B, then we're going to use this alignment chart. Okay, so the relationship between the K, which is the effective length factor, and G's, which is GA and GB, is based on this alignment chart. We are having, this is a very famous alignment chart based on Jackson and Moorland alignment chart, okay, in 1976, which are produced in, this is different figures actually in the commentary. You are going to find that A, this is for side sway not prevented, unbraced frame, which is our case now. I'm talking about it. If you look to this alignment chart, you're going to find that point A is moving relative to point B laterally, because this is like, as we said, side sway not prevented. However, the other case, which is side sway prevented, which is we are supposedly found it in raised frames, we're going to find that the point A and point B, they are not moving to one another. They are not moving to one another. They are like only buckling off the column itself under like load. So here we are having like delta, some relative movement. We have the force, axial force, and we have rotation as well. But here we are under the braced condition. We are assuming that there are some bracing that is going to control, okay, or they are connected at bracing at the end that is going to control the lateral movement. We have theta only, and we have the vertical force. Okay, so this is the alignment chart. We're going to put here GA starting from 0. Okay, let's erase here. This is GA, which is starting from 0 and ending with infinity. And also for B, it is starting from 0 to infinity. And in the middle, we are going to find K, which is starting from 1 and ending with like infinity, which is 20 here, because there is nothing more than this. Yes, we are not to use, of course, this 20. We're not going to reach it. But anyway, what is interesting here, for side sway not prevented, whenever side sway is there, we are starting from 1. Means that our K is always larger than 1. But if we are talking about braced frame where side sway prevented, we are going to start with 0.5 always. And we are going to limit it up until 1. Okay, so this is major difference between side sway prevented and side sway not side sway prevented and side sway not prevented. Okay. Okay, now again, we are under the title of like side sway not prevented. This is what we are talking about. Okay, so this means that we are going to get the K based on this alignment chart. We're going to look what is GA based on the summation of I over L for columns at this point. If we're talking about point A, and we are going to repeat the same process here at point B. Okay. IL for columns over the summation of IL for girders at each point. And then we're going to, if it is here, we're going to like connect between the two, the value of GA and the value of GB, and then you are going to intersect the K axis with a point. This point is considered to be your K. Okay, so this is what we are having here. This is what we call it the alignment chart. Commonly, whenever that we have a hinged condition, so you are going to find G equals to 1, okay? And if we are having the pin condition, then you are going to find that G equal to 10. So simply, in order to making your life easier, whenever you have fixed end condition, G equals to 1. Whenever you have pin end condition, G equal to 10. Okay, this is for the alignment chart for the case of unbrazed frames, or we can say side sway not prevented. Okay, and this is again, as I said, this is what we're going to do for GA and GB. GA and GB. We're going to calculate the summation of I over L for column over I over L for beams. This is for this point. And we are going to do the same, okay, here for this point. Then these two values are going to be used for the alignment chart in order to obtain the value of K. Okay. Okay. Now, till now it is very good, and this is the common effective length KL for frames for side sway permitted. This is commonly used. It's a common like values. As you can see always that these points, they are relative to one another. They are not going to move. Okay. Wait, please here. Okay, so as you can see here, this is, yes, this is the case. I'm sorry, this is the case here. Not all of them, they are side sway permitted. Actually, they are like we are having these two cases, they are side sway permitted because the point here and here, they are moving to one another. So we're going to find that KL is larger than 2 in this case here. Okay, this is unbrazed frame, hinged base. But if we have unbrazed frame that is fixed base, you are going to find that this point is moving toward this, or relative to the bottom or the base, and you are going to find that our KL is going to be in between L and 2L. Okay, so this is hinged base, this is fixed base. However, for the common effective length KL for frames, side sway not permitted. So again, this is side sway permitted for this case. But we have another case that I'm describing here, which is the brazed frame. This is the brazed frame. As you can see, the 2 points are not moving to one another. We have bracing here. So the K is going to be within 1 or less than 1. KL between 0.7 L and L if the base is hinged. However, if the base is fixed, we are going to have the buckling length to be between 0.5 and 0.7. Okay, always whenever that we have the fixed base, you are going to find that KL is going to be less than the hinged base. Okay, now that's very nice. And I think that we are ready now to go to the second part, which is side sway not permitted or brazed frame. Even that I have mentioned about some cases here, I should have put these two cases actually here, but anyway, we understood it now. So in this case, the definition, I want to highlight or place emphasis upon one thing here, because this part actually I have like taken it from Salman and Johnson book, because it's important also and written in ASIC, in ISC. the definition of the braced frame. What is the meaning of braced frame? Because maybe we put braces, but they are not working properly. They are not adequate to provide the lateral support for the system that we are using, right? So we need to know what is the meaning of braced frame definition. So according to AISC C1.31, this is where you can find the definition. Okay, the lateral bracing is, or the braced frame is, the one in which lateral, take care of the words here, lateral stability is provided by diagonal bracing, shear walls, or equivalent means. So we have like diagonal bracing. This is example of diagonal bracing here that you can see, cross bracing here, okay, or something like this, or shear walls, okay, like shear walls like this, whether they are masonry or reinforced concrete or steel plate, whatever the type. So the vertical bracing system must be adequate. This is a key word here. Adequate means that we need to design here. Chapter 6, okay, is going to provide for us the design of stability bracing, as I'm going to talk about it later, especially for beams, as determined by structure analysis. To prevent buckling of structure and to maintain the lateral stability of the structure, including the overturning effects of drift under the factor loads, okay, this is what the word adequate means. To prevent buckling of the structure and to maintain lateral stability. So two things here that we need to take care of, which is prevent buckling, okay, and lateral stability. Because if we are going to have lateral loads, sorry, let's go here. Yes, if we have like lateral loads, then the bracing is going to provide like support against these lateral loads, and in the same time it should provide the stability for the ends of the element under consideration, I mean the column. Note that a vertical column in a braced frame would have no side sways movement of its top relative to its bottom. That's right. This means that this point should not move relative to this point. Okay? This is what we mean by adequate braced frame. Okay? And note about braced frame, we have two types of braced frame. Okay? So the braced frame must not resist only the tendency to sway under action of lateral loads, but also the tendency to buckle, as we said, lateral loads and buckling. Let's go back here to prevent buckling, as I said, and to provide lateral stability. That's very important. So here it is the same. We are going, or this bracing needs to provide like stability against buckling, okay, or becoming unstable, and lateral loads as well. Bracing to stabilize a structure against vertical load is called stability bracing. Yes, we call this stability bracing. Bracing to stabilize structure against vertical loading. Take care, we're talking about vertical loading, because whenever that we have vertical loading, let's go back here. For example, if we have like vertical loading, there is tendency, if the loading is unsymmetric, there are a tendency of this braced frame even to go laterally. Okay, it is going to move laterally. Okay, if we didn't provide this kind of lateral bracing, okay, the adequate lateral bracing. So if the loading is unsymmetric, then we're going to find that our structure is going to move laterally. So here, bracing that is going to stabilize a structure against vertical loading is called stability bracing. Stability bracing. Okay, Appendix 6 of the AISC specification, stability bracing for columns and beams, covers this type of bracing, and we have two different types or categories, relative and nodal. So we have like two different types of stability bracing. One called relative, where that the bracing is connected to the elements themselves. This is a plan, by the way. This is the plan. So this is the column here. This is actually relative and nodal. It is going to be explained in the beam chapter, but only I want to like provide to you an idea about what is the meaning of stability bracing. So we have like relative and nodal. The nodal means that the points are connected to rigid support, external rigid support. However, relative means that we are putting some relative bracing. So if we're going to talk about like the elements here, for example, yes, if we are talking, this is considered to be like relative bracings. But if I'm going to provide here something like this and here something like this is considered to be nodal bracing. Okay, effective length of columns in case of continuous structure, side sway not permitted. This is the common one that we can say, or we can see here. Always KL, as can be shown, always less than 1. I mean that K here, K is less than 1. Okay, because we have pen or fixed or pen fixed, or it is like in a continuous structure or frame, but it is braced frame. So we are going to find that our KL is always less than L, as you can see in all cases that we have. So this is the end rotation unrestrained. This is end rotation fully restrained in this case. And we have one end restrained, other unrestrained, which is fixed here and hinged here, and partially restrained at each end, which is this case. Okay, so I think that this is the end of our video for today. I hope that you have understood what I have explained for today. Please, I think that the dose of information here is high, and you need to go back and check what I have said and try to stop the video at different times and try to do your assignment by yourself, especially for the examples, and go through the main ideas again. Thank you very much for listening, and see you in the next video.